This is the Discovery Files podcast from the U.S. National Science Foundation. It has long been imagined that robots might be useful for performing tasks for us, from robot housekeepers to the repetition in manufacturing, or exploration in environments that may otherwise be dangerous to humans. As next-generation technologies such as robots are developed, operational challenges come to light that need specialized attention to be figured out. This includes challenges such as the way machines might see, whether it be by camera or some combination of other sensors, or the limits of computational power that something like an automated vehicle needs to perform the real-time reactions necessary to operate safely. We're joined by Hao Zhang, Associate Professor of Computer Science in the Manning College of Information and Computer Science at the University of Massachusetts Amherst, where he directs the Human-Centered Robotics Lab and works to create innovative computational algorithms that help robots operate and adapt over periods of time while collaborating with humans and other robots. Professor Zhang, thank you for joining us today.
Hi, Dave. Thank you for having me here. It's a great pleasure to be here, and I look forward to a great conversation and hopefully share some insights with you all.
I think you will for sure. There's a lot of interesting robotic stuff we're going to get into in the next little bit here. So thinking about robotics, how did you first become interested in the topic?
So everything actually began during my childhood. I was absolutely fascinated by robot cartoons and TV shows like Transformers, Gundam, and Knight Rider. And they were not just entertainment for me. They provide me a window into a world of robotics, where I saw endless possibilities and also opportunities in this future robotics technology. These TV shows portray robots as more than just machines. They have incredible intelligence. Some of them, they have personalities, they have emotions, and many form close bond with humans. So this made me think about the potential for robots to not only being treated as machines, but also interact with humans in some meaningful ways. These TV shows simplify many complex concepts and made them accessible and also exciting. So, they introduced me to the basic principles of robotics without making it feel like a boring lesson. As I got older, my interests only become stronger as I saw more potential and, how cool robots are. Then I started, reading more books on robots and assembling DIY kits and toys and, joining robotics competitions and later pursued formal educations in robotic related fields. So this experience formed generally a lifelong passion and set me on the path to becoming a roboticist and also a professor so that, I can create some real robots just as amazing.
You mentioned this idea of robots interacting with humans, and your lab there is the Human-Centered Robotics Lab. So I would like to ask you, how do you define human-centered robots?
Human-centered robotics is still an interdisciplinary field, and it dedicates to creating robots that can naturally interact and collaborate with both humans and also other robots, and hopefully in a way that is safe, reliable, intuitive, and also effective. Human-centered robotics aims to augment human capabilities rather than replace them. We receive a lot of critiques whether they will just take people's job away. That's actually not the goal of the roboticists. So, here are several new aspects of human-centered robotics. For example, designing human-centered robots to work with humans require a user-centric approach. So that will ensure interactions and collaborations are intuitive and effective to humans. And the robot must be able to also learn from humans and also adapt to their teammates within specific contexts of tasks and environments. It's also crucial that robots operate safely around humans. So we must incorporate the safety measures and ensure reliability to build the trust between humans and robots, and also to prevent potential hazards. It leads to actually a bigger new aspect. So we'll need to really address important ethical issues for human-centered robotics. So for example, privacy, fairness in decision-making, emotional impact, liability, and regulations. So these considerations generally help ensure that robotics technology can be used in a responsible way and benefit society as a whole.
Okay, so thinking about how humans and robots are interacting, I know one of the challenges that I hear about with, say, automated vehicles is computer vision and this idea of them being able to see things. So can you talk about some of the challenges with robotics perception?
You generally mentioned two terms. So while computer vision and robot perception are related, they actually have some slightly different definitions. Computer vision focuses specifically on analyzing visual data such as images and videos from cameras. And in contrast, robot perception uses a broader range of sensors to understand not only the environment and also the robot state. And just give you an example. So, a robot may use these visual cameras as well as its so-called proprioceptive sensors, such as like wheel encoders and also accelerators to localize itself. This is like a robot perception problem. And essentially, we can consider like computer vision is a key component of robot perception, but robot perception has a wider scope. So, and you are right, like robot perception is not easy. So the first challenge is due to the environment variability and the changes. So robots must perceive their environment consistently despite changes. For example, you mentioned about like self-driving car. So, self-driving car must handle various environmental conditions, including, driving during daytime or like midnight, in different weather conditions or across like 4 seasons in order to, drive safely and consistently. And the second challenge is caused by the sensor degradation and also failure. Sensors can be obstructed by mud. When you drive a car, it's likely you have something that's going to cover your sensor. And sensors themselves, they can also fail. These situations generally impact the robot's ability to reliably perceive its environment and must be addressed. So this is another big advantage in like robot perception. And another challenge is to integrate perception with this common sense and the logic. For example, recognizing a tree in the sky is unlikely reflects the common sense or like logic. So, which robots may leverage to actually prevent or like reduce the perception like errors. Of course, there are like many other technical challenges that are classic. So for example, like a sensor fusion from multiple resources, that's classic problems in robot perception, and also like real-time perception. So real-time is really important in robotics, especially when we control like high-speed robots like a UAV.
In one of your lab's videos, there demonstrates a model that's kind of following a person into a classroom, I think, or into a couple different rooms. So I wanted to ask you, what are the vision strategies, I guess? Cameras, infrared, 3D mapping. There's a lot of different things that are going on. How are you able to make this possible?
First of all, you're right. So choosing the right strategy for robot perception is actually an important design decision that actually depends on the specific application and the environment. You mentioned about like robots following a human, and the other very widely used application like is 3D mapping. When it comes to this type of vision or like robot perception applications, there are several options that you may consider. Creating 3D maps as an example. To create a 3D map, we actually can choose single camera, and using a single but moving camera can actually provide a 3D map. So this is generally called the structure from motion or like a monocular mapping. So however, this 3D map tends to be like a rough and lacks accuracy in the map, and they typically lack scale information. And some other option that is also popular is to use these color depth sensors. So sensors like, Connect for Xbox, they use infrared projector and receiver to estimate depths. They can be used to create a 3D representation of the environment, and that can be further used to create a 3D map. However, because the depth estimation from infrared is typically not very accurate, and the generated maps are often contain noise and may not be as good or accurate as desired. And additionally, these color depth cameras based on infrared, they typically have a short sensing range, and they do not work outdoors under direct sunshine. Another very popular option is this LiDAR. So LiDAR sensors, they offer the highest accuracy for distance measurements, and they can provide very detailed and precise 3D maps. But LiDAR sensors are actually much more expensive than the other two options, and they require like a substantial computing power to process this large amount of like a point cloud data. In summary, each of the options have their own advantages and disadvantages. It really depends on the task and applications. But the general rule is, if we consider like an indoor 3D perception, no matter for mapping or to follow a person, we typically choose these color depth sensors. They work pretty well indoors and provide sufficient accuracy. And when we want to sense long distance in outdoor scenarios, especially under direct sunshine, we typically choose LiDAR sensors. Robotics perception is inherently like a multi-sensory problem. We typically actually use all the sensors together, especially at the time when we develop a prototype. And then we'll later decide which sensor is more effective for a specific application.
So thinking about the environment as majorly impacting how you're going to go about using it. In your current work, you're looking at multiple robot strategies. What are the advantages of a team-based approach? Why might it be better to have multiple robots to get a task done?
That's actually a great question. So a team-based approach offers many advantages. And here I'll discuss like three key aspects and key benefits. The first one is the scalability and parallelization. Many robotic applications naturally involve the use of multiple robots. This includes like industrial and warehouse automation and, environmental exploration and monitoring and, connected autonomous driving. And the team-based approach can easily scale up by, adding more robots to address an increasing workload. And the tasks actually can be executed simultaneously by multiple robots. The computational workload required to execute, for example, some AI algorithms can also be distributed across multiple robots. So that's the first advantage. And the second advantage is like efficiency and productivity. So when you consider about like a team-based approach, it actually can leverage diverse capabilities of different robots and humans and also their like specialized skills to more effectively solve complex problems and large-scale problems. So for example, in this search and rescue operations, multiple robots can cover much larger area more efficiently than a single robot. The third benefit is this redundancy and the reliability. Robots, when we deploy them in the real world environments, they always fail because of wear and tear over time. So if one robot fails, other robots, other teammates can continue to perform the task and, ensure the mission completion. So this redundancy enhances the adaptability and also the robustness of the entire team. This team-based approach can also greatly reduce the risk of mission failure, due to the malfunction of individual robots.
I want to pivot a little bit for the next question and ask you about more programming strategy. So you have a career award and you're currently working with this concept of adaptation. What are the challenges, or how are you using things like AI and machine learning to teach robots how to adapt to new scenarios?
So these traditional robots, they are designed for specific tasks and, typically in these isolated environments. So if you consider this industrial robot arms used in this vehicle manufacturing assembly lines, so those are the traditional robots. So they are typically limited to the scenarios for which, they have been programmed and trained. And in contrast, when we consider about the human-centered robots, they must operate in this dynamic, uncertain, and open environments. And they must interact with diverse human users. They need to handle this different like new scenarios they probably never encountered before. And to achieve this, robots generally need to be more intelligent and adaptable. And for this purpose, generally like AI or artificial intelligence provides a natural approach to enhance their capability and make the robots smarter. So my career award generally focuses on developing like a novel paradigm for like robot adaptation that is called robot reflection. Robot reflection is defined as the artificial metacognitive capability of a robot to introspect and also adjust its adaptation process. For example, we have developed methods for this self-aware adaptation in context. So that generally like allows robots to compute adjustments or like control offsets based on continuous monitoring of both the environment and also the robot's own functionalities. So for example, we mentioned, if one robot sensor fails, then the robot actually can smartly switch to other sensors or combine information from a set of other sensors. So that's one of the example. That sensing capability or sensing results will be used to make sure the control of the robots or the behavior of the robot is consistent, even the robot has some failures. And another example is where right now like developing this robot rehearsal as a technique that enables robot to imagine and plan for new scenarios without the need of physically experiencing those scenarios first. And generally, the goal of my NSF Career Award is to allow robots to effectively address these changing and novel scenarios and adapt throughout the robot's lifetime. That is also called lifelong robots.
At the beginning of the conversation, you mentioned kind of the ethical needs in programming here. As you're trying to make them self-reflective, what are the challenges making sure there's an ethical safety built into it?
On the AI perspective, we need to have some methods, for example, to remove all the personal information from the robot processing process. So, robots have a suite of sensors, for example, like cameras. That camera just similar to some security cameras. If you consider like a home assistant robots, the robot actually need to record a lot of videos from the user or from the home environments. And then the question is, how can they, from the AI perspective, how can really like remove all this sensitive personal information from the whole robot perception and decision-making process and make it more like a private to the user? So that's one of the considerations. And then they need to consider about, when we put the robots into our society, shows humans, they actually follow social norms. So, when we get into the elevator, we always face the doors. So the robots, generally, we want the robot to have these capabilities to follow these social norms. That generally means, a working robot is not sufficient. The robot should also, perform this, have these satisfactory behaviors that follow like human social norms so that human actually interpret the robot's behaviors. So that's another level of consideration. Another level is these regulations or like, the policies need to really to make sure we have the robots for the good, right? So, and, we consider about self-driving car, it takes a long time to figure out the regulations. And the self-driving car can generally be considered as like a part of human-centered robots, although the user may not be necessary to interact with the self-driving cars. But, if we consider this tightly coupled human-robot collaboration, just like humans working with other human teammates, then these regulations and the policies need to be in place, or at least we need to start thinking about it as a community.
I also want to ask you about your outreach program. It's called the Progress Program. Can you tell us a little bit about this?
Yeah, sure. I'm glad that you asked that. So Progress stands for Program for Robotic Outreach, Gender and Racial Equity in School and Society. The primary goal of Progress is to develop a high quality like robotic outreach and education that serves the needs of a diverse and inclusive society. And, we offer lectures, we offer robot demonstrations, presentations, workshops, and summer camps to like K through 12 students and teachers, and as well as to educate, the general public. We also develop robotics curriculum with a collaboration with actually elementary school teachers to promote STEM learning for younger kids. Since my own interest in robotics began like when I was a kid, outreach is really my passion. And through Progress, I hope to inspire and train the next generation and make robotics more inclusive and accessible. So basically, I want to break down barriers and open up opportunities for everyone, especially for kids.
Exploring the idea of having the summer school and younger kids in the lab environment, what kind of things are you showing them to get them inspired? Like what kind of devices do they get to interact with?
It's a combination of lectures and hands-on projects. So lectures, they are like the younger kids. So we actually have several lectures talking about the history of robots and show some cool videos about the state of the art of the robots. And then we talk about, we discuss each of the key components like sensor, computer, mechanical components. We generally go through all these basics. And we use Lego robots, like robot kits, as our tool for students to do their projects. And, when we talk about each robot components, we have the corresponding smaller project for the kids to explore that specific aspects of robots, like sensing, moving the robot from one point to another point. And then over time, we have this relatively bigger projects that actually have students design the projects. We generally give each team of students a scenario and they need to come up with a solution. For example, we maybe have, now we are in the environment with many boxes in the center of the room, and then we want the students to program robots to move all the boxes to the corners. And, students may also have a competition on these projects. Or we may create a maze. That's a classic project for educational robotics courses. So we also create a maze and let the students to program their robots, design their robot sensors and computers for the robots to navigate throughout the maze. So typically this kind of workshop is like 20 to 40 hours.
Very cool. It's got to be very satisfactory to see those kids getting it in their head what robotics can be and figuring out how to do it and kind of inspiring the next generation that way.
Yeah, exactly. I feel that's one of the biggest rewards for a professor. They have the knowledge, they also have the resources, and thanks to the support of an SF. So, and then, we can sort of inspire our passion to the next generation.
So the last question I want to ask you, thinking about your work over the next couple of years, what are you excited to be working on in the future?
I believe the future of robotics must be incredibly exciting and full of potential and new opportunities. And, for the community, there are several key areas to watch. The first area is control GPT or robot GPT. That is also one of my biggest passion. So just as ChatGPT has revolutionized these chatbots for human level communication, and then this question arises. So can we build a control GPT to perform robot controls? Or can we build a robot GPT for a full stack robot operations from perception to reasoning to robot control, all of that? Is that possible? That's an open question, and I feel that's very exciting. For the whole community, lowering entry barriers is the big next step. So to really deploy robots in real world, we must make robots more accessible and also cost effective in order to allow more people and organizations to use robots or participate in this exciting field. With robotics, we build robots, but eventually we really want our work can benefit people and also benefit the society. And from my own research, there are several areas to watch. For example, the innovations in humanoid robots and the physical human-robot interaction and collaboration, and the swarm robots that includes a large number of robots. They are generally pushing the boundary of what robots can achieve. And I feel those technological frontiers are really exciting and worth the time to explore. And the last one, we brought this question several times. That's the ethical and the societal integration. So we must, develop regulations, standards, and frameworks generally to guide the responsible development and the use of robotics, in order to address this ethical, societal, and even safety concerns. And I hope my research is helping to shape the future in meaningful ways. Thank you.
Special thanks to Hao Zhang. For the Discovery Files, I'm Nate Potker. You can watch video versions of these conversations on our YouTube channel by searching at NSF Science. Please subscribe wherever you get podcasts, and if you like our program, share with a friend and consider leaving a review. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.